Cell 1. In this cell, we're diving into the importance of analyzing the historical affordability of housing in New York City. Understanding this topic allows us to explore a wide array of implications for policy evaluation, risk management, demand forecasting, equity insights, scenario planning, and market regime detection. Each of these areas plays a crucial role in how various stakeholders interact with the housing market. As we examine policy evaluation, we can see how changes in interest rates, zoning laws, rent regulations, taxes, and subsidy programs directly influence housing affordability. For policymakers, tracking these relationships helps them gauge the effectiveness of their strategies. On the other hand, lenders, investors, and developers are particularly interested in how deteriorating affordability could signal risks, such as increased defaults or a drop in buyer demand. Moreover, understanding historical affordability can help forecast future trends, even if precise predictions aren't always accurate. The shifts in affordability guide us in understanding how buyer engagement may fluctuate over time, which is invaluable for anticipating market reactions. Additionally, equity and distribution insights revealed through affordability trends allow us to pinpoint which groups or time periods have experienced significant challenges, illuminating when and where the need for support is most acute. Scenario planning is another critical aspect, as historical data provides realistic boundaries for stress tests. For instance, exploring what might happen when interest rates rise significantly or prices decline enables stakeholders to prepare for various market conditions. Lastly, identifying market regimes through the lens of structural breaks, like those seen in 2022, helps inform strategy and policy decisions. As we transition to the next cell, we will likely focus on applying these insights into practical analyses, examining specific historical data to elucidate trends and their implications on current and future housing affordability. Cell 2. In this cell, we are pulling and processing various economic data series to create a well-structured dataset for further analysis. This step is crucial because it lays the foundation for our modeling efforts, allowing us to observe how different economic indicators interact over time. We start by defining a date range from January 1st, 1990 to the present, utilizing the FRED database to pull data on mortgage rates, real estate prices, unemployment, rent indices, and personal income, all specific to New York City. The toMonthly function will convert any weekly data to a monthly format, ensuring consistent time intervals across our dataset. Each of these variables is given a key name for easier reference, stored in a dictionary, so we can efficiently loop through and download the relevant time series. After obtaining our raw data, we specifically focus on transforming the weekly mortgage rate data into monthly averages. This is done through resampling, which helpfully takes care of the varying frequency of data points collected. The resulting data frames for each economic indicator are then merged together using an inner join, meaning we'll only keep the months that have complete records across all selected series. It's worth noting that this approach can lead to certain pitfalls. For instance, while we might expect data from all series to perfectly align, some are updated less frequently than others, which can create gaps. However, we've taken care to forward fill to maintain continuity, preserving the last valid observation for variables that may not be reported monthly. Before finalizing the dataset, we ensure it has a consistent month-end frequency, which is vital for time series analysis. The result is a data frame ready for analysis, although it's important to remember that some series have limited historical data. Notably, our series on New York City metro prices only starts from July 2016, which effectively limits how far back our combined data can go. As we move forward to the next cell, we're likely to dive deeper into analysis and modeling, potentially applying machine learning techniques to explore the relationships within this enriched dataset. The groundwork we've laid here is essential for building insights and drawing conclusions from the interactions of these economic indicators. Cell 3. In this cell, we are developing a practical payment-to-income affordability index, a crucial tool for understanding how manageable housing payments are in relation to income. This index not only highlights the financial feasibility of homeownership, but also serves as an essential indicator for potential buyers assessing their capacity to afford a new home. The process begins with defining key parameters, like a down payment of 20% and a loan term of 30 years. These elements are fundamental, as they reflect standard practices in the real estate market. Next, we incorporate an escrow component, which accounts for taxes and insurance as a percentage of the home price. This allows us to create a more comprehensive estimate of monthly payments, often referred to as PITI, principal, interest, taxes, and insurance. Once we have our monthly payment figured out, we can compare it to the buyer's monthly income. This comparison allows us to compute the affordability index, where the formula essentially takes the payment amount and divides it by the income. The result is presented as an index, with higher values indicating more affordable conditions. An important insight here is that as the burden on the homeowner increases, meaning their payment takes a larger share of income, the affordability index falls. This relationship is critical for understanding how changes in market conditions or individual circumstances can impact housing affordability. It's also worth noting that the accuracy of this index depends on the assumptions we make about variables such as interest rates, tax rates, and insurance costs. So being mindful of these factors is essential. As we transition to the next cell, we will likely apply this affordability index to real-world scenarios, enabling us to visualize its implications for prospective homeowners and the broader housing market. This will not only enhance our understanding of affordability metrics, but also provide practical insights into the financial decisions individuals face. Cell 4. In this cell, we're calculating monthly mortgage payments and related financial metrics for properties in the New York City metro area. This analysis is crucial because it allows us to evaluate housing affordability by comparing monthly payments with household incomes. The workflow begins with defining a function that computes the monthly payment based on the principal amount borrowed, the annual interest rate, and the duration of the loan in months. If the interest rate is 0, the function simply divides the principal by the number of months, which provides a straightforward way to estimate payments. However, for positive interest rates, it employs a standard formula to calculate the monthly payments, incorporating compound interest over the term of the loan. Next, we establish the down payment percentage at 20% and a rough estimate for tax and insurance, which amounts to 1.5% of the home price annually. These figures help in determining the loan amount and overall monthly expense. Using data from our data frame, we extract the property prices and the mortgage rates, adjusting the latter effectively for computation by converting it from percentage to a decimal form. The cell then performs calculations to determine the total monthly payment, which includes both principal and interest, as well as tax and insurance. We also create a proxy for household income based on per capita income, scaled to account for typical household sizes in the area, giving us a monthly income figure. This is essential for assessing the burden of housing costs on households. To quantify this burden, we calculate a ratio of total monthly payments to monthly income, offering insight into the financial strain relative to earnings. By analyzing this ratio between the years 2000 and 2019, we derive a baseline burden metric, which sets the stage for evaluating how contemporary burdens compare to historical standards. Finally, the data frame is cleansed of any missing values, and we display essential columns to provide a snapshot of our processed data. This sets the groundwork for our next cell, where we will likely explore how changing factors affect housing affordability over time, further deepening our understanding of this vital issue. Cell 5. In this cell, we're utilizing Plotly to create a line graph that visualizes the Housing Affordability Index for the New York City area. This graphic is important because it provides a clear and interactive way to analyze how housing affordability has changed over time, giving us insights into economic trends that can impact residents and policymakers alike. The process starts by selecting our data, specifically pointing to the HAI column, which represents the Housing Affordability Index. We set the x-axis to use the data frame's index, ensuring that our time component is accurately represented. The title, NYC Area Housing Affordability Index, higher equals more affordable, effectively communicates the key takeaway that a higher index value indicates better affordability. As we move through the code, one key step is the update of the layout dimensions for our figure, where we specify that the width should be 1100 pixels and the height should be 500 pixels. This thoughtful consideration makes the graph more visually appealing and easier to interpret. Finally, calling fig.show displays our plot, allowing us to interact with the data and gain deeper insights. It's also worth noting that while visualizations are extremely powerful, they rely on accurate and well-structured data, so ensuring our data frame is correct is crucial. A common pitfall to watch out for is misunderstanding what the indices represent. Here, they correspond to specific time points. Looking ahead, the next cell may dive deeper into analysis, or possibly contrasting this affordability index with other economic indicators, further enriching our understanding of housing trends in the area. Cell 6. In this code cell, we're visualizing the Housing Affordability Index, or HAI, while marking significant events in its time series through regime shading. This technique helps us to understand how specific periods, like the COVID shock and post-rate shock phase, impacted housing affordability. To tackle this, The code begins by importing the necessary Plotly library, which is excellent for creating interactive visualizations. It then extracts the relevant HAI data from a data frame, ensuring that any missing values are removed for cleaner analysis. The next step involves creating a figure object from Plotly, where the HAI series is plotted over time. The use of a line graph allows us to easily observe trends and fluctuations in the index. Defining the regimes is where the visualization strategy really comes into play. Two specific periods are highlighted: the COVID shock, spanning from March 2020 to June 2021, and the post-rate shock phase starting March 2022 and extending to the latest available data. The code uses a loop to add vertical rectangles on the plot for each regime, giving a clear visual indication of these critical time windows. These shaded areas, with their soft opacity, allow the underlying data to remain visible, while still drawing attention to the context in which that data was generated. The layout adjustments finalize the visualization, setting titles for the axes and ensuring the overall dimensions work well for presentation. The final output is an engaging graph that not only displays the HAI over time, but also situates it within key historical contexts. As we look forward to the next cell, it's likely that we'll dive deeper into interpreting this visualization, discussing potential implications of these regime changes, and possibly exploring additional analyses or predictive metrics regarding housing affordability. Cell 7. In this cell, we're visualizing the relationship between mortgage rates and housing affordability using a scatter plot. This is crucial because it helps us understand how changes in mortgage interest rates can impact a buyer's ability to afford a home, which is particularly important in today's economic climate. The code creates a scatter plot with the x-axis representing the 30-year mortgage rates and the y-axis representing the Housing Affordability Index, or HAI. By employing a trend line using ordinary least squares, we can clearly see the correlation between these two variables. The intention is to illustrate how affordability fluctuates as mortgage rates shift. When we look at the resulting plot, a pattern emerges. During times when mortgage interest rates hover around 2.7% to 3%, we notice a significant spike in the HAI. This indicates greater affordability, making it a more favorable environment for homebuyers. Conversely, as mortgage rates rise above 7%, we see the HAI plummet, suggesting that homes become substantially less affordable. It's important to consider how these insights can affect potential buyers and investors alike. As you interpret the plot, keep in mind that external factors, like economic conditions or changes in consumer demand, could also influence this relationship. Failure to account for these can lead to misleading conclusions about housing trends. Looking ahead, the next cell will likely delve into a deeper analysis of these findings, perhaps exploring implications for policy or offering predictive insights based on historical trends. This sets the stage for understanding how we might navigate future shifts in the housing market. Cell 8. In this cell, we're creating a scatter plot that examines the relationship between price and affordability in the New York City area, specifically using the Housing Affordability Index, or HAI. This visualization helps us to understand how housing prices relate to what residents can reasonably afford, providing valuable insights into the local real estate market. The plot is generated using the Plotly Express library, which simplifies the task of crafting interactive visualizations. We're plotting HAI on the vertical axis against the NYC metro area prices on the horizontal axis. This setup allows us to see at a glance how changes in price correspond to shifts in affordability. A trend line, specifically ordinary least squares regression, is included to better illustrate any underlying trends between the two variables. As we look closely at these connections, it's essential to consider the variables involved. The Affordability Index provides a quantitative measure of how accessible housing is for average earners, while price reflects the current market conditions. Together, these metrics can highlight disparities or trends that may signal whether housing is becoming more or less accessible over time. It's also crucial to remember that while this analysis offers visual clarity, there can be limitations and assumptions baked into both the data and the methodologies used. For instance, outliers could skew our understanding, and different neighborhoods may not behave uniformly. In summation, this scatterplot serves as a foundational tool for understanding real estate dynamics in New York City. As we move to the next cell, we can anticipate exploring further aspects of this analysis, possibly diving deeper into data interpretations or examining other characteristics that affect housing affordability. Cell 9. In this cell, we're diving into the concept of feature importance using permutation importance, which helps us understand the contribution of each feature in our model's predictions. This is crucial for interpreting the model and identifying which variables really matter, especially in complex datasets. The first step here involves utilizing the permutation importance function from the sklearn library. This function takes our trained model, along with the test data and test labels, to assess the impact of each feature on the model's performance. What's interesting about this method is that it evaluates how well the model can predict the outcome when the values of a particular feature are shuffled, breaking the relationship between that feature and the target outcome. By repeating this process multiple times, we've chosen 50 in this case, we aim to obtain a robust estimate of feature importance. Next, the results of the permutation importance are stored in a perm variable. This includes the mean importance scores that we will analyze further. We then create a pandas series called per-imp, organizing these scores by the corresponding feature names, which allows us to easily sort and visualize the most significant features. By sorting them in descending order, we can quickly identify the top contributors to our model. As we display the top 20 features, it's important to note that this analysis assumes that our features are independent. If features are correlated, the interpretation of their importance can become more complex, potentially leading to misleading conclusions. This insight into feature importance not only enhances our understanding of the model, but also sets the stage for refining it in future steps. Next, we might consider how these insights can influence model improvements, or even lead us to explore feature engineering options that enhance our predictive power. Cell 10. In this cell, we're diving into feature importance, a crucial concept that helps us understand what factors are driving our forecast. This exploration is particularly significant because it provides insights into which variables are influencing our model the most, thereby highlighting potential areas for further investigation or refinement. Here, we start by organizing the feature importances calculated from our model. The variable imp is created as a pandas series that pulls in these importance scores. This score essentially indicates how valuable each feature is in making predictions. The higher the score, the more significant that feature is to the model's decision-making process. We sort these importance values in descending order and focus on the top 20 features because these are often the most impactful for understanding the model's behavior. We then visualize this information using a horizontal bar chart, which makes it easier to quickly grasp which features rank highest in importance. The figure is customized to enhance clarity, with specific dimensions for better visualization of the data. This bar chart does more than just list features. It provides a visual signal about the relationships between features and model predictions, which becomes vital as we interpret our results. However, we must keep in mind a crucial caveat. The negative r-squared value we're about to encounter suggests that our model may not generalize well. This means that even minor adjustments in the training window could dramatically shift the importance of features, potentially leading to instability in our model's predictions. As we move forward, this understanding of feature importance will guide us in making informed decisions about feature selection and model tuning. In the next cell, we'll likely explore the implications of these importance scores in more depth, laying the groundwork for optimizing our approach to improve model performance. Cell 11. In this cell, we're diving into predictive modeling to forecast housing appreciation indicators 6 months into the future. This step is crucial as it allows us to analyze various economic factors like mortgage rates and unemployment, which can give us insights into housing market trends. To start, we create a new data frame that includes a shifted version of our target variable, the housing appreciation indicator, leading us 6 months ahead. This gives us a clear target variable to aim for in our predictions. We then enhance our dataset through feature engineering. For several economic indicators such as mortgage rates and metropolitan prices, we generate lagged versions at 1, 3, and 12-month intervals. This captures short-term fluctuations while also providing a broader context of slower-moving trends. Also, we calculate monthly changes in the mortgage rate and year-over-year changes for price and rent metrics, which helps in understanding immediate and historical shifts in the market. Afterward, we ensure our dataset is clean by dropping any rows with missing values resulting from these transformations. Next, we extract our features based on certain criteria, focusing mainly on the lagged values and calculated changes. We split the dataset into training and testing sets to simulate a real-world scenario where we'd want to predict future values based on historical data. Specifically, we use a time-based split to maintain the chronological order. Then, we fit a random forest regressor model using our training data. This ensemble method is powerful for capturing complex relationships in the data. and we set specific parameters to balance performance and prevent overfitting. Once the model is trained, we predict the housing appreciation for our test set, and we evaluate the model using metrics like mean absolute error, root mean squared error, and R squared. These metrics help us understand how well our model performs and where it might fall short. Ultimately, the insights gained from this predictive modeling process may guide decisions in the housing market. In the next cell, we will likely explore the implications of our model's predictions, perhaps visualizing the results or examining additional metrics to refine our understanding further. Cell 12. This cell evaluates the performance of a model we've been working with, specifically examining its R-squared value, which is a key metric in assessing the fit of our regression model. Here, seeing a negative R-squared is quite unusual and indicates significant issues, often signaling that our model fails to predict outcomes better than simply using the mean of the observed data. The core of this analysis hinges on the fact that our training data primarily covers a period before 2018, with very limited information from recent years due to data filtering. Given that we are testing during the unprecedented conditions of the COVID-19 pandemic and a period of economic upheaval characterized by rate shocks, we expect our model to struggle. The random forest algorithm, although powerful, often finds it challenging to adapt to these new regimes when it encounters data that is vastly different from its training set. A negative R-squared value suggests that the model is not only inaccurate, it's actually worse than what you would achieve with a basic average. This can be a significant takeaway, highlighting the importance of having training data that adequately represents the range of scenarios we want to predict. In practical terms, the implication for our project is clear. As it stands, this model has little to no predictive value, urging us to reconsider our approach and the data used for training. Looking ahead, this realization sets the stage for the next cell, where we will likely explore alternative strategies or different modeling techniques to improve our predictions and make sense of the challenges. Cell 13. In this cell, we're visualizing how the COVID-19 pandemic has radically altered housing costs and the overall cost of living in New York City. This analysis is particularly relevant, given that the changes in housing affordability indicate deeper economic shifts affecting many urban areas. We're starting by creating a data frame that combines actual housing affordability index values with their predicted counterparts. This is done using the PD data frame function, which collects the data into a structured format that's easier to work with. The drop-on method ensures that any missing values are removed, preventing them from skewing our analysis. Next, we generate a line plot to visually represent the actual versus predicted housing affordability index over a 6-month period. This is created using Plotly Express, which offers a clean and interactive way to explore our data. We set the title of the plot to emphasize the key comparison we're making between the actual and predicted values. It's important to consider that the actual index reflects real-world data, showing how residents have experienced affordability challenges, while the predicted index illustrates a model's expectations, which may or may not align with reality. The discrepancies we see in the graph can reveal critical insights about how accurately our model is capturing the shifts in the housing market. As we examine this plot, keep in mind the potential for outliers or unexpected trends caused by the pandemic's impact. These may indicate areas for further investigation. Looking ahead, the next cell is likely to build on this visual comparison by offering some analysis of the discrepancies we've identified, potentially exploring the factors that could have influenced the actual versus predicted values. This deeper dive will be essential for understanding the nuances of the current housing market in a post-COVID world. Cell 14. In this code cell, we're summarizing the accomplishments of our project and reflecting on the insights we've gained around affordability indicators. This is essential, as it helps us understand where we stand in terms of predictive capabilities and what we can derive from our data analysis thus far. We've essentially built a replicable affordability index pipeline, which allows us to draw meaningful insights from various housing and economic metrics. By working through multiple frequencies of data, we've transformed weekly mortgage rates into a monthly average and aligned them with other key indicators, like prices, unemployment, and rent trends. This alignment is crucial because it ensures that we're not just working with isolated data points, but rather creating a coherent, monthly panel that speaks to the same time frame. The observed trends reveal significant relationships between these variables. For instance, as mortgage rates increase, our affordability index tends to decrease, indicating a strong negative relationship. Similarly, rising home prices are associated with declining affordability. Additionally, it's interesting to note the notable regime shift around 2022, which appears to represent a critical affordability cliff. When we looked into forecasting, we found that our model produced a negative R-squared value. While this might initially seem discouraging, it actually serves as a valuable indicator of structural changes in the market, particularly surrounding the disruptions caused by COVID-19 and the subsequent changes in interest rates. Despite the challenges in producing reliable forecasts, we've laid the groundwork for conducting scenario analyses. This opens up a range of what-if questions, like exploring how an increase in mortgage rates could impact payment burdens, or examining the effect of a 10% or 20% drop in housing prices on overall affordability. Importantly, we've also identified key features contributing to our model, such as lagged rent CPI, income, and unemployment rates. While these factors seem to provide useful explanations for trends, we must be cautious, as their importance isn't stable enough to establish them as definitive drivers without further validation. Looking ahead to the next cell, we'll likely explore specific scenario analyses based on the insights we've gathered, applying our previous findings to examine potential future outcomes in the housing market. This will allow us to deepen our understanding of affordability dynamics and better position ourselves in the face of uncertainty. Cell 15. This cell marks the conclusion of our current analysis. It's crucial because it encapsulates everything we've worked on, emphasizing the significance of our findings and how they fit into the larger context of our project. Now, stepping back, we can appreciate how every preceding cell has been guiding us towards this endpoint. Throughout our exploration, we've incrementally gathered insights, applied various methods, and examined our data closely. The final output serves as a comprehensive representation of our efforts, showcasing the results of our computations and analyses. What we've seen so far is not just a collection of numbers or statistics, but a narrative built from our data. It's important to reflect on the decisions we made along the way, how we processed information, which variables we prioritized, and the assumptions that underpinned our findings. One of the key takeaways is that each step was intentional, allowing us to build a robust understanding of our subject matter. Looking ahead, this completion doesn't signify an end, but rather an opportunity for evolution. The insights gained here can propel us into more advanced analyses or broader applications. Whether we're considering further experiments or developing new questions, the groundwork we've laid in this project will be invaluable. In the next cell, we will likely expand on these findings or explore a related area, adding even more depth to our understanding. So let's prepare to carry this momentum forward into our next adventure in data analysis.